Okay, so here we are going over the back side of our covalent ditto, or worksheet, as people like to call it now, and we are writing Lewis dot diagrams. And we are doing so with the idea that we're trying to make stable electron configurations. Atoms are using each other to become stable. So the first step in writing Lewis dot diagrams for covalent structures is understanding that electrons are going to have to be shared here. So hydrogen, how does it work? Okay, and I know we did some of these before. Now I know we did these before, but I want to review. So hydrogen has one valence electron, so we draw one dot. Okay, another hydrogen has another valence electron, and we draw another dot. And we can see that both of these, by sharing, have the what? Same number of electrons, and that number is 2. If we look at the configuration of hydrogen, it's 1, and it wants to gain 1 more to have the same configuration of helium. I can't say this enough. So back to where we were, hydrogen has a configuration of 1, and when it gains 1 more, in this case sharing 1 more, it feels as stable as helium. The reason why atoms bond is they get stable to feel like a noble gas configuration. Having 2 electrons makes the configuration stable. They don't become helium, but they become as stable and low energy as helium. So having 2 electrons for hydrogen is stable. Everybody else wants to have this octet rule, this 8 here. We want to fill that 8 for everybody else to be as stable as these noble gases. So we did bromide. Bromide, okay, as 1, 2, 3, 4, 5, 6, 7 valence electrons. And how do I know it's in group 17? You have to know your valence electrons. And another bromide also has 7, and you can see it's a nice match. By sharing, both of these guys feel like they have 8, which is the octet rule for all other elements. Okay? Now, before we continue, I want to determine 2 other things today that is brand new. Number 1, I'm going to call this the polarity of the bond. This is brand new. Okay? Polarity of the bond and the polarity of the molecule. These are brand new concepts. Now, polarity means, do we have differences? If somebody is, let's say, polar, okay, you've heard the word bipolar. So if someone's polar, okay, they may have 2 sides to them. They may be happy one day and very angry the other, or they may have multiple personalities. I'm not saying that anybody in here has these issues, maybe a few, but polar means that you clearly have differences, okay? And as a person who's bipolar, they're going to have differences in their personality. They're not going to be the same. So when we talk about polarity, we're talking about differences across either the bond or the entire molecule. And understand, we're talking about molecules, not crystal lattices. So the first thing is to identify the bond. Absolute first thing. Now I look between H and H. Now both H's have the same electronegativity. One H has electronegativity of 2.2. The other H has an electronegativity of 2.2. Remember, electronegativity is the attraction for electrons. So because of that, we see that these electrons, because these both have the same attraction, because they're both the same element, these electrons are going to be shared right down the middle. Shared right down the middle, which means they're shared evenly. And if they're shared evenly, we would say that no one side or another has more electrons from this pair. This pair of electrons is equally distant to this hydrogen and to this hydrogen. So no one has more electrons than another. Therefore, we would say that the bond is a non-polar bond. There's no difference. We both have the same number. So this is a non-polar bond. Now, if you're a nonpolar bond, that means that your molecule, okay, if it only has one bond, has no shot to be polar. So, the first thing we're discussing is the polarity of the bond. Now look at bromide. Now bromide is the same element, so it's also going to have the same electronegativity. Now I don't know the number, it's probably somewhere close to 2.6 is my guess, but the bottom line, they're both the same element, so these electrons are shared evenly or equally down the middle. So we would say that this is a non-polar bond as well. Now make sure you say bond, just don't say non-polar, because there's something called molecules as well. All right? So if you can see, it's very clearly, if you have the same electronegativity, you will have, you will have the same, or you'll have a non-polar bond, because very similarly, being the same element means you're going to have the same attraction for electrons. Okay, so we did O2 yesterday, or at least we did Friday. Let's do O2 again. Oxygen has 6 valence electrons, so we write them. The first step is to write out all the valence electrons. 1, 2, 3, 4, 5, 6. We'll make one bond apiece. This oxygen has 6. 1, 2, 3, 4, 5, and 6. Now the first thing you do is make one bond. Put out all the valence electrons. Oxygen is 2-6, by the way, so it has 6 valence electrons. The outermost electrons are valence. We've already learned that. And we put out all the valence electrons. And what we do is we evaluate. And after you put the electrons out, make a bond. A bond is a pair. Now evaluate that. When I evaluate, I count 1, 2, 3, 4, 5, 6, 7. This oxygen is sharing 7 by sharing. By sharing, it has a total of 7. Okay, and this one, for the same reason, by sharing, it feels like it has 7. Remember, this number needs to go to the 8, not the 7. So what we're going to do here is the only thing we can do is add another bond. So I'm going to bring another bond up. So I bring another pair up. And now by doing this and making another bond, I evaluate again. And here I have 2, 4, 6, 8. And this side has 2, 4, 6, 8. Now both of them feel like they're 2-8. Oops, 2-8. The octet rule has been satisfied for both of these. And we would say that oxygen has a double bond because each bond is a pair. But what kind of bond is it? Is it a polar or non-polar? And I'm asking someone out there to tell me, what is it? Say it aggressively. Say it again. Not good enough. Yes, yes, and yes. Okay? You're right. It's a non-polar bond. Why? It's the same element bonded to the same element. Yes, you can do that. If it's the same nonmetals, you would say that the bond is non-polar. Has to be because they're sharing electrons equally because they have the same electronegativity. Each oxygen is 3.5 in their rating for electronegativity. So these electrons are being pulled equally by each one, so nobody has any differences. Okay, moving on to nitrogen. Nitrogen, okay, there are 5 valence electrons. So the first step is to put out the 5 valence electrons. All right. And I always put out one bond. Now what do? Put out the valence electrons, make one bond, and now we're going to evaluate. And when you evaluate, you're going to see 2, 4, 6 for this end, 2, 4, 6 for this end. Not close. Remember, nitrogen is 2-5. It wants to be what? It wants to be an 8 to be as stable as a noble gas. So this is not good enough. So what we're going to have to do is we're going to have to make another bond. We evaluated that each nitrogen doesn't have an 8, so we're going to make another bond here. And when I do so, Evaluate again. And when I evaluate, I see that this end feels like now 2, 4, 6, 7. We're getting closer, but we're still not the 8. Each end wants to feel like it has 8. So the second bond got us closer, but not good enough. So the only thing you can do is, guess what? That's right, Reese. You add another bond. He was saying it telepathically. What do you want from me? Okay. So you add another bond. And there it is. And each one now has 8. And that's how we do it. Okay? Very simple. Okay, now, so this N has 3 bonds. What kind of bond? It has 3 covalent bonds, but they're sharing equally or unequally? Well, I would say because each N has the same electronegativity, that these are being shared equally, and all 3 of these bonds are nonpolar. The bond is nonpolar. Okay? Very, very simple. Hopefully that makes some sense. All right, let's go to a more advanced structure that maybe you started having some problems. All right, let me just try to move this guy to the side maybe. No, that didn't really work. Okay, doesn't matter. Let's go to CH4. Now I'll put CH4 over here. So we have C. No, I don't want that. C. And you may say, well, how do I know how to bond these? Because some people might say, well, C, maybe it goes like this. C bonds to H, C bonds to H. You say, oh, how does that work? Remember, a dash is 2 bonds. Well, the one that has more valence electrons to fill is usually the one that's in the center, but a lot of this is going to be just from experience. I put the carbon central because when I look at carbon, its configuration is 2-4. It's got 4 valence electrons, which means it can make 4 bonds. Now, why do I know it can make 4 bonds? Well, because it wants to have 8. So it would need to have an electron from 4 other things. Those 4 other things are hydrogens. So these hydrogens come by, and they put another electron around. And this would be the Lewis dot diagram. I put out all the valence electrons, pair them up for at least 1 bond between the elements, and now I evaluate. And when I evaluate, I get carbon having the 8, right? It wants to be 8. Octet rule. Each hydrogen wants to have 2 because in its energy level, 2 electrons make it work. Okay, now the question is, what kind of bond do I have here? What kind of bond do I have between the H and the carbon? Okay, no longer is this bond nonpolar because carbon and hydrogen do have different electronegativities. Okay, I believe carbon, okay, I'll just put it over here, carbon is 2.6, hydrogen is 2.2. So if I just blow up one of these bonds, okay, honestly, the more electronegative element, who is stronger, puts that pair closer. So this pair is actually closer to the carbon to the hydrogen. And because of that, they are sharing unequally. So they're sharing unequally. This is important. This is brand new. Why unequally? Because the pair has been pulled closer to the carbon. And because the electron density from the bond is closer to the carbon, this carbon is said to give a partial negative charge. This is a weird thing called a partial symbol. Okay? Now it's a partial negative charge because the electrons weren't plucked away. That'd be an ionic. There was no transfer. Remember, we're still sharing because both of them are pretty strong, but we're sharing unequally because one of the two, the element that's more highly electronegative, is pulling that pair closer. Now the side that has the electrons pulled closer is the partial negative side, and the side that has the H pulled kind of away is the partial positive. This side has more electron density than this side, My friends, in chemistry, this is called a polar covalent bond. Why is it a polar bond? Because we're sharing unequally, and you have what we call differences. What does polar mean? You have happy and maybe angry type of behavior from one person. You don't know what to expect. But on this side, we have two different behaviors. When things were non-polar, they were the same on both sides. Nobody had more electrons than another. So when you have two different nonmetals, the bond will always be polar. We should write that. Okay? So on the top somewhere, nonpolar bonds equal the same nonmetals bonded. And when we got polar covalent bonds, these are what? Different nonmetals. Now you should understand why. You have to understand. Same nonmetals, they what? They share equally, so that both sides of the bond do not have more negatives or positives. They're the same. But in different nonmetals, they share the electrons unequally, which makes one side different than another. And that's what makes poles. Okay? All right, so we would say that CH4 called methane has 4 polar bonds. All right, 4 polar bonds. Now, let's go to number 6. All right, let's go to number 6. CHI3. Looks confusing. Who goes in the middle? Well, the carbon's going to go in the middle because hydrogen has 1 valence electron. All it needs is another to fill it. Iodine from the what? Halogen group has 7. It only needs 1 electron to fill its energy level. So these guys are terminal. Carbon, as we talked about, has 4 valence electrons. So it can be central. Okay, it has more electrons to fill to get. It needs 4, so it can bond to multiple things, where these guys can only bond to one thing. So here comes my H. And it doesn't matter where you put the H's, there's 3 of them, but each H brings an electron. And each H now is what? Stable and happy as helium because it has its 2 electrons by sharing. Iodine has 7 valence electrons. So I have to show all the non-bonding electrons. And there you go, I'm done. Put out all the valence electrons, make at least 1 bond apiece, and what do? You evaluate. Each hydrogen has 2. It's stable. There's 2 electrons in the first energy level. Iodine, by sharing, feels like it has 8. And carbon, by sharing 4 electrons and 4 from another, feel like it has 8 as well. Okay, so this is the correct Lewis dot diagram for this compound. My question to you is, what are the bonds? What are the bonds here? Is it a polar bond, non-polar bond? Where are they? Well, the bonds, okay, inside here, let's make this colorful. So these bonds, believe it or not, are all going to be polar bonds. Why are they polar bonds? Because they're 2 or more different electrons being shared. Oh, in this case, I should say there are 2 different elements being shared. So therefore, okay, they're shared unequally. If I was to blow up the carbon and iodine bond, okay, probably iodine is a little more electronegative, so that pair would be closer to it. Okay, so they're sharing unequally. They're two different atoms. Okay, so now we should have a clear understanding what a polar bond and a nonpolar bond are. Now, as I talked about before, we just did the bond. Now I want to do the molecule. Understand the difference. Don't just say polar, nonpolar. Are we talking about the bond? Are we talking about sharing electrons equally, which would be a nonpolar bond? Or are we talking about sharing electrons unequally, which would be a polar bond? All right, that's a big difference. But what is a polar molecule? Well, a polar molecule means that one side of the entire molecule has more electrons than another. So if this was a molecule, this would mean if it was polar, it has a lot more negatives or electrons on one side than the other. So we would call the side with more electron density, you're right, the partial negative side, and this side the partial positive side. Notice the positive side is a side with the less number of electrons, not necessarily protons. So polar molecules, all right, are going to have this positive and negative side to them. Now, in order to have a positive negative side, think about it. What's going to create a scenario where I'm going to have more electrons on one side of the molecule than another? What did we just talk about? In order to be a polar molecule, you need to have something that creates an unequal distribution of electrons. Well, that is going to be, you need to have a polar bond. In order to be a polar molecule, write it down, you have to have a polar bond. Check out number 1, H2. It only has a non-polar bond. It has nothing else. So therefore, this molecule is non-polar, as well as having, it's a non-polar molecule. So this doesn't have any polar bonds. So therefore, this molecule has nonpolar bonds, and the molecule is nonpolar. Look at number 2. It has one bond. The bond is a nonpolar bond. It doesn't have any unequal distribution, so therefore this molecule is also a nonpolar molecule. And we could say the same for 3 and 4. All right. What about 5? 5 has 4 polar bonds. Okay. 5 has, let's make it bigger. 5 has 4 polar bonds. And you may say, okay, it's got a polar bond. So according to my laws, all right, according to my laws, I should be right. Well, we have to consider something other than polar bonds. Okay? So there's another thing. If you have a polar bond, that's great. But 2, we have to consider whether the molecule is the same all around. So to be a polar bond, okay, it has to be different all around. What does that mean? It means you have to be asymmetrical. Let me explain. Let's look at our methane again. Now we look at our methane, CH4, bringing that over here. It's got 4 polar bonds, therefore it's sharing electrons unequally. But because it's the same all the way around, because we say it's symmetrical, we would say that these polar bonds cancel out. Let me explain, okay, another way. All right, here's a methane. Here's a C. Here's the H. Here's the H. Here's another H and the final H. It's put in the valence electron. Okay, carbon is more electronegative, so that pair is going to be pulled closer to the carbon. Okay, so we would say that the more negative side of the bond is at the carbon side. Let's put negatives here. The positive end, where electrons kind of get pulled away but not transferred, is here. Now, we call these dipole moments. And I want you to think with me what they are. They're basically a flow of charge. We go from the positive to the negative. So what I'm going to draw is 4 arrows. The positive side goes to the negative. The positive side goes to the negative. The positive side goes to the negative. What they represent is 4 arrows. Think with me for a second. I have 4 equal forces. All right? And they're all pushing in. If these arrows are all the same size, and the size of the arrow is indicative of the difference in the electronegativity, think with me. Wouldn't this force cancel out this force? They're just opposing forces. If 2 trucks are pushing on each other in these 2 directions, they would cancel themselves out. These 2 forces cancel themselves out. And overall, you have 4 forces cancel themselves out, and we would call this a nonpolar molecule because it is symmetrical. If it's symmetrical, think with me for a second. If the electron distribution is symmetrical, you're not going to have a negative or positive side. For it to be polar, you need an asymmetrical distribution of electrons to create that. So a polar bond helps create the asymmetry or the unequal distribution of electrons, but the shape of the molecule is about what number 2. If the molecule shape 3-dimensionally is not the same all the way around, it would be polar, but this one is the same. It does have symmetry. And I have a weird way of saying it. I have 4 polar bonds being shared unequally. So it has a chance to be polar, but because it's symmetrical, we say that the symmetry, or we say that the unequalness of these electrons is equal in all directions. I'll say it again, it's weird. The unequalness of all 4 of these bonds is the same in all directions. And that's the same thing as saying they cancel themselves out. Now, if you don't like that way, let's go find another way to explain it. Let's go on to the next one that we did. CH3I. This has 4 polar bonds, right? So this has a chance to be polar. To be polar, you have to have polar bonds. Check. Is this the same all the way around? The answer is no. It is asymmetrical. Therefore, because it's asymmetrical, this is a polar molecule. Now, why is it a polar molecule? It's a polar molecule because you've got something different that doesn't cancel. Let's do the arrows again. Okay, if we do the arrows, watch. I have, oops, probably too much. Okay, let's go down. I just went blank. Okay, let's do the arrows again right here. I have a positive going to a negative. Who cares the positive? And then I have 3 arrows doing this that represents these 3. But wait a minute. The difference in electronegativity with the iodine is different. In fact, it's more electronegative than the carbon, so this arrow goes this way, goes toward the negative from the positive. So you can clearly see, hopefully, that this would cancel, but this doesn't. And what we have is an overall dipole moment showing the negative side of the molecule is here. If you don't like any of that, here's what you do. Does this have polar bonds? You would say yes. Is it the same all the way around? Yeah, if it's the same all the way around, the polar bonds would cancel. However, it's not the same all the way around. If it's asymmetrical, then it is a polar molecule. Okay, let's try one more together, and I want you to look at these, and I want you to evaluate, after you do your Lewis dot diagrams, the molecule. So H2S, let's do it. S goes in the middle. It has more valence electrons. So 1, 2, 3, 4, 5, 6. H. comes here, H comes here. Okay, notice we evaluate. When we evaluate, sulfur now has 8, each hydrogen has 2, and that's a good Lewis dot diagram. What kind of bonds does this have? You would say polar bonds. Now, what about the molecule? It does have polar bonds, so the first necessary item you need to have is, does it have polar bonds? Yes, that's satisfied, but is it symmetrical? Well, you may think it is symmetrical, and if you think it's symmetrical, then this would be a non-polar molecule. The polar bonds would cancel themselves out. It's the same everywhere, but when you have lone pairs of electrons, these lone pairs of electrons actually repel these downward. So what actually happens is anytime you have unpaired electrons above the central atom, it bends it downward, bends the bond downward into something called a bent shape, which is very asymmetrical. So even though you may think the way I wrote it that this would be very symmetrical, meaning the polar bonds would cancel and this would make a nonpolar molecule, the lone pairs on a central atom, and I repeat, always bends the other bonds downward. Why? These are electrons. Electrons repel other negatives, and it repels it down. So central unbonded electrons always bend the other electrons downward into an asymmetrical shape. So this is asymmetrical, and you have polar bonds. This is a polar molecule. I want you to finish this sheet, look at the key, figure out the bonds and the molecule. By the way, the dipole moment, the overall, okay, this would be, sulfur is more electronegative than the hydrogen, so you would have an overall dipole moment going up. And if you're not quite sure about these arrow things, I'll continue on. Please, I'm going to have for homework 2 small lectures to review and some more of these to do. But from right now, finish the rest of these and evaluate. Again, whether they're polar or nonpolar, okay, in terms of the bonds and the molecule. The molecule, you have to think 3-dimensionally. Good luck.